Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last lecture we started module 6 on radial migration of fibers in yarns. So, we have talked about general fiber path in yarns, how to characterize this fiber path that we have discussed. Then we talked about a fiber element, how to characterize this fiber element. We used cylindrical coordinates and also we derived certain basic relations among the angles to characterize the fiber path inside the yarn. Then we classified yarn structural models based on two differential equations, and then from there we defined what is radial migration of fibers, and we started Taylor's ideal migration of fiber model. We introduced 4 assumptions of Taylor's model, and based on those 4 assumptions we derived the fundamental equation of ideal migration. The fundamental equation of ideal migration took this form: tan square alpha is 1 plus tan square beta k square tan square beta minus 1. This was the fundamental equation of ideal migration or fundamental equation of Taylor's model. Now we will discuss about K. What is the meaning of K? We would like to know more about this K. K was equal to P period of migration multiplied by packing density 2 times n number of fibers in yarn cross section. S is the cross sectional area of a fiber, Z is twist, which is constant. So, this was equal to K. Now, let us think about this quantity n times S, this one. What is this quantity? Number of fibers in yarn cross section multiplied by cross sectional area of a fiber. So, this is the cross sectional area of all fibers when they are parallel. That means, this is basically the substance cross sectional area of a parallel fiber bundle. The concept of substance area we introduced in module 2. So, this NS we can write as substance cross sectional area of the non twisted fiber bundle. In module 2 we used capital S to denote substance cross sectional area. Here we use the same symbol with subscript 0 to denote the initial non twisted fiber bundle. And also in module 2 we have introduced this relation where capital T naught denotes the fineness of the bundle, parallel fiber bundle, and rho is fiber density. This T naught is related to final yarn by this relation where this denotes yarn retraction. Yarn retraction was discussed in helical model of fibers in yarn, that was probably module 4. Right. So, this NS T naught by rho that is equal to T by rho into 1 minus retraction, right. T, capital T is yarn fineness. We know the basic relation between diameter and fineness of yarn, that is your d square is equal to 4 times capital T pi mu rho. This is yarn diameter d, capital D, T is yarn fineness, mu is packing density, rho is fiber density. So, T by rho pi mu d square by 4. If we substitute here T by rho, then what we will obtain? Pi mu d square 1 minus retraction by 4, that is your Ns, right. This Ns we substitute here. So, what we obtain is P, period of migration, into packing density 2 pi mu d square 1 minus retraction by 4. This is your Ns and this is your Z. Right. So, 2 p mu divided by pi mu d square 1 minus retraction. Let us write it further. K is equal to 2 p mu pi mu d square 1 minus retraction, right. Now, this mu cancel out, right. And where is Z? Z must be here, Z must be here. This Z was missing from here, so this Z must be here. So, 2 p mu pi mu d square 1 minus retraction into Z, 2 p mu pi mu d square 1 minus retraction into Z, right. Okay. This we can further write 2 p pi d z 1 minus retraction into d. In a nice form, 2 p by d 1 divided by 1 minus retraction into what is pi dz? Yarn twist intensity tangent of beta d, module 2 tangent of beta d. Right. So, this is what is K. Period of migration has a dimension of length, millimeter. Yarn diameter has also having length dimension, millimeter. So, these two length dimensions cancel out. Yarn retraction dimensionless, pi dz kappa twist intensity is also dimensionless. So, K is a dimensionless quantity. Often said in theoretical research work, dimensionless quantities are very important. They signifies something about the structure. right. Now, we come back to the fundamental equation of radial migration, and we would like to know the domain of that expression. So, fundamental equation was tan square alpha tan square beta plus 1 k square tan square beta minus 1, where k is equal to 2p by d 1 by 1 minus retraction into 1 by tangent of beta d, right. Left hand side is a square quantity. That means this denominator must be greater than 0. So, k square tan square beta minus 1 must be greater than 0. What is k? 2 p by d 1 by 1 minus retraction 1 by tangent of beta d, here also tangent of beta square minus 1 must be greater than 0. What is tangent of beta d? That is equal to pi dz. Pi dz. And what is tangent of beta? 2 pi rz. So, what we see is that this pi cancel out, z cancel out, so 2r by d, so basically 4. So, what we are left with 4 p r d square 1 minus retraction minus 1 greater than 0, right. So, 4 p r d square 1 minus this must be greater than 1. So, r must be greater than this. So, r must be greater than a small quantity. D is very small, P is small, retraction is also small. So, this expression gives you a very small value, however, it is a value, and r greater than this. That means there is a problem. What is the problem? Problem is the fundamental equation is not defined for a small value of r. So, there is some problem in this expression. What is the meaning of this? Meaning of this is something like this. This is the radius and this is the axial length of yarn r zeta. Fiber is not starting from 0 because r is greater than a small value. So, probably the migration starts from here. So, it goes there, come back, it is not touching the axis, a small distance is left. This distance is this d by 2 square by p 1 minus retraction, again it goes come back. So, in this grey color region, migration is not taking place. This is the meaning of this. So, what is the fiber path? According to this, tan square alpha, tan square beta plus 1 k square tan square beta minus 1. Now, what is tan alpha? dr by d zeta square. What is tan beta? 2 pi r z r z. So, dr by d zeta is plus minus one. So, dr is equal to plus minus 2 pi r z square plus 1 2 pi r z square minus 1 into d zeta. So, if we integrate dr or else d zeta plus minus dr by this expression 2 pi r z square plus 1 k square 2 pi r z square minus 1. So, if we integrate this, then we will be able to obtain the path of a migrating fiber. However, this integration does not have an analytical solution, elliptical, it is elliptical integral. This is one problem. Problem number 2, fiber path is not defined at a very small radius. So, far The fundamental expression of radial fiber migration as per Taylor's model have two problems. One, it is not possible to obtain the fiber path of a migrating fiber analytically. Second, fiber path is also not defined at a too small radius. That is why we introduce two approximations. So, we introduce two approximations so that there will be an analytically possible fiber path and it will be defined at all radius. So, the first approximation, period of migration is very long. We think that, so let us assume that period of migration is very long. What does that mean? Slow migration. If period of migration is very long, k is proportional to p. So, k is very high. So, this is our first assumption. Second, we introduce, we assume that tan square beta is much less than 1, a very small value, much less than 1 for all radii R. So, we here introduce two approximations and we like to know what is the implication of these approximations. So, we come back to the original fundamental equation, tan square alpha is equal to tan square beta plus 1 k square tan square beta minus 1. Okay. Tan square beta plus 1 is sec square beta. Sec square beta is 1 by cos square beta. So, 1 so we can write 1 by k square sin square beta minus cos square beta. Sin square beta is equal to 1 minus cos square beta. Right. So, k square minus k square plus 1 cos square beta. K is very high, so k square is very high, k square plus 1 very high quantity plus 1 remains very high. Approximately equal to k square. Then it becomes k square into 1 minus cos square beta, so k square sin square beta. So, we used here first approximation and we would like to use second approximation somewhere. Let us write 1 as sin square beta plus cos square beta k square sin square beta. Then you see tan square alpha is equal to 1 by k square 1 by 1 plus cot square beta. Let us go to the next page. So, tan square alpha is equal to 1 by k square into 1 plus cot square beta. So, 1 plus tan square beta. Now, you see tan square beta is much less than 1. 1 by tan square beta is much greater than 1, right. Very large quantity plus 1 remains that large quantity. So, this becomes k square tan square beta. So, tangent alpha is equal to plus minus 1 by k tan beta. This is known as approximated equation of ideal migration. This equation is defined for all radius. So, one problem is over. This expression is defined for all ready. What was the second problem? Second problem of the fundamental equation. The analytical solution of the integral was not possible. Let us see if it is possible here. So, tangent alpha is equal to plus minus 1 by k times tangent beta. What is tangent alpha? Dr by d zeta, and tangent beta is 2 pi r z. So, we can write dr by d zeta is equal to 1 by k times 2 pi r z, right. So, d zeta is equal to plus minus k times 2 pi r z into dr, right. Now, if we integrate this, what we will obtain? We will obtain zeta is equal to plus minus k 2 pi z into r square by 2 plus c, where c is an integral constant. Right. So, zeta is equal to plus minus k pi z r square plus c. So, this integration is possible. So, the two problems associated with the fundamental equation, one was analytical solution was not possible, second it was not defined for very small radius. So, in order to avoid those two problems, what we thought, we considered two approximations. One is k value is very high, slow migration, period of migration is very high. Second, tan square beta much less than 1. Based on these two, we found that it was defined, the approximate equation was defined for small radius, and also analytical solution is possible. So, we are in this way, by introducing two approximations, we could solve the problem associated with the radial migration of fibers. But this equation gives additional problem. What is that problem? Let us see. Let us consider r is equal to d by 2. R is equal to d by 2. So, plus minus k pi z d square by 4 plus c. Now, look at this equation. When r is equal to 0, this must be equal to 0. So, c is equal to 0. So, this is equal to 0. So, what we find is that plus minus k times pi z d square by 4. What is k? K was 2p by d into 1 by 1 minus retraction into 1 by tangent of beta d. Tangent of beta d is pi dz into pi z d square by 4. Now, this pi is cancel out, z cancel out, this d and d square cancel out, these two. So, what we obtain is that p by 2 into 1 minus this. This is a problem because at d by 2, this value must be equal to p by 2. Why? Because if this is r, this is zeta, if this is your d by 2, then this distance is p by 2. So, at r is equal to d by 2, zeta d by 2 must be equal to p by 2. However, it is not. It is not so. So, we need to correct the approximated equation. So, correction to approximated equation. Let us say tangent of alpha is equal to plus minus 1 by k prime tangent of beta. Instead of k, we consider k prime. How is the relation between k prime and k? K prime is equal to k into 1 minus retraction. So, k was 2p by d, 1 minus retraction 1 by tangent of beta d into 1 minus retraction. So, 2p by d 1 by tangent of beta d. Right. So, then what will be your tangent alpha? So, by using this we are able to solve, which is now defined at this p and this when r is equal to d by 2. So, zeta, let us say zeta value. So, dr by d zeta is equal to plus minus 1 by k times, we have to write it. So, 2p by d 1 by tangent of beta d into tangent of beta. Okay. So, let us see what is happening in the right hand side. 1 by tangent of beta 2 pi r z, tangent of beta d pi d z. Okay, that is equal to this. So, now the z cancel out, pi cancel out. So, what we see is plus minus this d square will be in the numerator. So, d by 2 d square by 4, this p will be in the denominator, that is all. So, d square by 4 p. So, yeah, then this r will be there. Yes. So, r dr is equal to plus minus d by 2 square by p into d zeta. So, let us integrate now. Integrate r dr, integrate plus minus d by 2 square by p into d zeta. Right. So, this integration will give you r square by 2 plus minus, this is constant, integration of d zeta is zeta plus say constant, integral constant. Right. So, what is zeta? Zeta is equal to plus minus 4p by d square r square by 2 minus c. Further, we can write is equal to plus minus 2p by d square into r square minus c. This is an equation of paraboloid. So, the corrected form of approximated equation fiber path is parabolic inside the yarn. So, according to Taylor's vision, ideal fiber migration, approximation and corrections. After doing this, we obtained that the fiber path inside the yarn is a parabola. How it looks like? Imaginatively, this is what is happening as per Taylor's model. Suppose a fiber starts from here, it touches the axis, red color, then it comes out to the surface, dotted line you can't see. From the surface it again goes inside, then it touches the surface, it comes to the surface, goes inside, then it touches the axis again, then it goes out. So, this path of fiber is parabolic one, and this distance is p by 2, this distance is p by 2. So, this is the total period of migration p. So, Taylor, as per Taylor's model, you can imagine how is the fiber path inside the yarn. It basically resembles a parabola. So, what was the form? Form was this, equal to plus minus 2p by d square r square minus c. When r is equal to 0, this must be equal to 0, this infers c is equal to 0. So, equal to plus minus 2p by d square r square. Now, as you can see, this is a very symmetric one. So, that is why we can take for calculations either plus or minus. Plus is outward, inward, as it is a symmetric. So, probably in order to establish the characteristics of migration, we can take any one positive. So, this equation, let us take the positive quantity only, because it is a symmetric one, r square. This we can further write p r square by d by 2 square. This r square by d by 2 square, let us consider this as capital Y, because we can measure this. D is measurable and R is also measurable by tracer fiber technique and all. So, then what do we find? Zeta is equal to p by 2, p by 2 into y, where y is equal to r square by d by 2 square. Now, we introduce characteristics of migration. How we can characterize migration experimentally? Generally, Taylor and his co-worker, they used three characteristics for radial migration. One, fiber mean position. Second is the amplitude of migration. Third is the intensity of migration. How intense is the migration, whether it is slow or fast, how. We would like to discuss about these three characteristics now. First, start with fiber mean position. Fiber mean position is defined by y bar is equal to y times d zeta by this. This is 0 to p by 2, this is 0 to p by 2. And what is y? Y was your zeta is equal to y times p by 2. So, y is equal to 2 zeta by p. This is how fiber mean position is defined. If we substitute zero to p by 2, y 2 zeta by p zeta 0 to p by 2. P is constant, 2 is constant, it will come out of integration. So, 2 by p zeta times d zeta 0 to p by 2 zeta 0 to p by 2. Integration zeta d zeta, zeta square by 2. Integration d zeta, zeta. So, 2 by p into p square by 8 minus 0. Here it is p by 2 minus 0. So, y bar is, here it is p by 2 and there it is p by 4. So, half. Y bar is equal to half. Mean fiber position is half. As it is a symmetric migration, there is a ideal fiber path, regular fiber path. So, mean fiber position is equal to half in Taylor's model, ideal migration. Second characteristics is amplitude of migration. Amplitude of migration is discussed in terms of RMS deviation. What is RMS deviation? RMS deviation is defined by y minus y bar square d zeta by d zeta. This is the definition of RMS deviation. So, what is your y? Y is your 2 zeta by p. What is y bar? Half square d zeta d zeta. So, if you integrate this, you will get this value. D is equal to 0.289 in case of this. There is amplitude of migration. The last characteristics is intensity of migration. Intensity of migration, we use symbol this, dy by d zeta. So, dy by d zeta square d zeta 0 to p by 2, 0 to p by 2. So, this is how we define intensity of migration. What was y? Y was 2 zeta by p, right. So, if you take the first derivative, substitute, solve this integration, you will see that this value you will get as 2 by p. You can try this. What we see is that if period of migration is high, J is less, slow migration. When P is very high, migration is happening very slow rate, intensity also indicates the rate of migration. So, the rate of migration is slow. You remember when we used approximations, two assumptions we considered, one is tan square beta much less than 1 and the second was about P is very high, then we talked about slow migration because of this. When P is very high, the migration is very slow. So, these three characteristics can be obtained from Taylor's model of migration. Now, the very important question, how is the correspondence between Taylor's migration model and reality, experimental results? Is it so that Taylor's model explains the experimental results very well, or is it so that Taylor's model fails to explain the experimental results? In order to find out this answer, lot of experiments were carried out and the comparison between theory and experiment is shown here. This region is the experimental region. Lot of yarns were tested by using tracer fiber technique, migration characteristics were measured, and in this region all experimental results fall, right. And what you see here, tangent beta is plotted here 2 pi r z, and this is tangent alpha into tangent beta. Two curves you see, one is the thick continuous curve, one is the dotted curve. Thick continuous curve is original expression, fundamental expression. What was that? Tan alpha was equal to plus minus square root of tan square beta plus 1 k square tan square beta minus 1, is not it? That was your original expression. Now, if we take the absolute value into tangent beta is equal to what? Tangent beta into this. So, this original, this is basically the original. So, the thick line denotes this expression original. For different value of k is equal to 20 this curve, k is equal to 30 this curve, and k is equal to 50 this curve, k is equal to 100 this curve. So, it is decreasing then increasing, decreasing increasing, decreasing increasing, decreasing slowly increasing. This is original. An approximated equation is shown by the dotted line. What was the approximated relation? You remember, tangent of alpha plus minus 1 by k prime tangent of beta. So, tangent alpha into tangent beta, and if we take the absolute value, then it becomes this. So, this was the approximated one, k prime. So, obviously, this is constant because k prime is constant. So, this expression is constant, that is why you see line parallel to x axis. This is a line parallel to x axis for k prime is equal to 30, k prime is equal to 50, k prime is equal to 100. So, this is about this curve, and the experimental results were obtained using tracer fiber technique. Morton's tracer fiber technique. What we see that there is a complete mismatch between the theoretical results and the experimental results. So, for the experimental results are concerned, when tangent of beta is increasing, this function is increasing. However, the theoretical results, original one decreasing then increasing, and approximated is constant. So, there is a complete mismatch between theory and experiment. Totally different trends. So, conclusion is Taylor's model could not explain the experimental results, they are totally different. Why is it so? Is there any possibility to correct Taylor's model and check with experiments? Is it possible to obtain a more precise model to explain radial migration of fibers in yarn? This we will discuss in the next class. Thank you very much for your attention.